All right, thanks a lot. Hi, let me turn on.
Hi. I won't talk so loud, so hopefully I won't destroy people's earbuds. My name is Brant Robertson. I'm a professor here at UC-HiPACC. Today I'm going to tell you about hydrodynamical coupling of mass and momenta into galactic scale outflows. This is work being done by my graduate student Evan Schneider, who's still at Arizona, where I used to be. And we're looking at the very detailed, kind of nitty-gritty physics of coupling the energy, momenta, and mass of large-scale galactic outflows with very small-scale pieces of gas, interstellar clouds, clouds in the exteriors of galaxies, to really understand how that eta parameter that everyone tries to match is really generated. What sets eta? Is eta just a number, or does it depend on density? Does it depend on velocity? How do you really understand the detailed physics that the simulations that most people have been talking about just really can't resolve? So we're trying our best to look into this. Oh, and let me just point out the archive number for the paper, if you're interested. So Conference on Galaxies would not be complete without pictures of M82, and I don't think we've had any. So that's my job to show you. I'm old enough to remember when Chandra was new, and in 2000 there was these really important results in Nature looking at the X-ray emission from around Chandra with 10 million to million Kelvin gas in the exterior, and then laying on top the optical R-band luminosity density of the galaxy. You can see this outflow in context from the star-forming region at the center where that very hot gas resides. And then, of course, you can go and look with ground-based telescopes at the H-alpha emission on large scales using narrowband imaging, and you can see the filamentary structure, this colder material that we're all very interested in, how that material got there, how is it traveling at large velocity, which it seems to be. So, star-forming galaxies, and not just M82, but many other galaxies exhibit this outflow. There's hot X-ray emitting gas. There's colder nebular line emitting gas. How did all of this material get there? And then now we have even more interesting observations from the ground, looking at CO and H2 material quite far out, moving at large velocities away from M82. This is work by Adam Leroy. So, how do we get this gas out here? So we've seen a lot of simulations where we've, blown various parts of galaxies apart and thrown them out into the halo. And we say, oh, well, that's an outflow, and we're matching the star formation rate to outflow mass loading ratios that are seen in low-mass galaxies. But why is that? How can we match those when we're not resolving the detailed structure of these outflows as observed? Shouldn't we look at the detailed physics of the way that mass and energy and momentum is coupled into the wind? Okay, so that's what we're interested in doing. So you might say, well, how does the hot phase, so the X-ray emitting gas, how does that originate? And really, we're all assuming the same thing, which is more or less what people have been assuming for a long time, that the input energy from supernova and star formation feedback thermalizes and then drives a hot outflow. Okay, so that's the main assumption, and there have been models of that process for 30 years now. But the comparably cold outflowing material is also out there at large radii. How did it get out there? Do we push it? Do we drag it? Do we throw it? Did it form there? Those are the kinds of questions that I'm interested in answering. So, in detail, we want to understand something about the multiphase material in the outflows. What sets the momentum of the gas? How much momentum is in this outflowing dense material? How does that compare with the momentum in the hot phase? Are they moving at the same velocity? I think these are all questions that we don't know the answers to. How long does it survive? These are all interesting questions about galactic scale outflows. So, we've seen many cosmological simulations where we've modeled, or even on smaller scales, let's say something about that. A little bit on galactic scales, the actual outflow from the galaxies. But of course, that process of putting material into the outflow starts on a very small scale. And people have also looked at this many times, and this is more what I'm going to talk about, the scales I'll be talking about. So here is a basic picture, and this is from a paper, an old paper by Klein, McKee, and Colella when I was in high school, and which means I'm old too now, I guess. So you have a dense cloud interacting with some hot outflow. Okay. So the context of this specific simulation was not galactic scale outflows, but the same kind of principle applies. You have some interstellar material that is relatively dense compared to a rarefied hot outflow that's moving supersonically with respect to the cloud. So then what happens? Well, you crush the cloud. I like to say you smush the cloud because that sounds messier, but you do something in cloud where you destroy it through shearing instabilities. And the time scale for those instabilities to destroy the cloud goes like the size of the cloud divided by the velocity of the shock times the square root of the density contrast between the cloud and the outflow. Okay, and people have looked at this in a variety of simulations. I'm going to show you some of the preceding work to provide some context, since some people may not be aware of these kinds of calculations. People were, interested in doing what Klein et al. Did at higher resolution with MHD, with cooling, mostly in 2 dimensions up until recently. Here's an early 3-dimensional calculation. So you can see some of the features of these simulations. You destroy the cloud. The basic picture seems to be there. Most of these simulations were interested in the destruction of the cloud alone, not so much what happened to the material after you destroy the cloud, which is a lot of what we're interested in when we talk about multi-phase outflows. There were some more recent simulations, and I really think this is all pretty amazing work that people have been doing. So these are all similar. People have done now adiabatic MHD simulations where you have 128 cells across the radius of the cloud, so very high resolution 3-dimensional simulations, looking primarily at relatively small regions around the cloud without cooling. You have this very nice work by McCord et al., people at Berkeley, looking at whether or not magnetic fields can help stabilize the cloud. And so when you're trying to put this very dense, comparably dense material at large radius, if you destroy that material through shearing instabilities, how do you get it out there? Well, one way you might be able to stabilize it through magnetic fields, and so that's very interesting work. And then recently, Scannapieco and Bruggen, and then also they've done some more work recently that I'll tell you some about. They did 3-dimensional radiative simulations with AMR, and what they were interested in doing, they were interested in how this material gets shredded. So what they did is they took a simulation of a box around the cloud, and they hit it with a wind, and then they moved the box along with the cloud. And that allowed them to resolve in some detail with AMR a maximum resolution of about 64 cells per radius of the cloud, just by moving their computational volume such that when they were resolving with high resolution, they didn't blow up the total number of cells that they were using, because that would be very expensive. Okay. So these are state-of-the-art simulations that people have been working on. So what is still needed? Well, I agree these are very high-resolution simulations. I think you need high-resolution simulations that capture radiative cooling, so there's some simulations that haven't gotten there yet. They need realistic initial conditions. Most of the simulations shown here just take a spherical cloud and hit it. But what happens when you hit a turbulent interstellar medium cloud with a hot wind? Does that change the picture at all? Also, you would like to capture the stripped and multi-phase medium at very large radius from the large distance from the initial cloud location. So you want to watch this stuff as it's stripped out and torn away from the galaxy. So you want to track the cloud material over many, many radii in distance from the initial cloud radius. Okay, but that's going to be expensive. So how do you do that? Well, our answer has been to just, throw away everything else and start anew. So many of you, they're world's experts in numerical simulation here, so I don't want to be too pedantic, but I would say that the largest supercomputers that we have in the world right now, the fastest, 2 of the fastest 3 and something like 6 of the fastest 10, the vast majority of their computational power are not in traditional CPUs. Okay, so I'll talk to you some about Titan. Titan's a system at Oak Ridge National Labs. It's the third fastest supercomputer in the world that we know about. It is, something like that you know So, it's been rated at something like 20-something petaflops per second, okay? But something like 18 of those petaflops are in GPUs that it contains. So lots of people like to brag about the amount of telescope time they get or the amount of computing time they get. But imagine if you got 50 nights on Keck and you were clouded out 40 of those nights. That's like using a system like Titan or Stampede and only using the CPUs. And so what we would like to do is use a supercomputing code that actually takes use of those GPUs and leverages them to do fast calculations. So for her thesis, my student Evan Schneider, who's amazing, you should all be fighting each other to hire her when she applies for jobs, she's written her own GPU-based static mesh hydrodynamical simulation code called CHOIA, that stands for Computational Hydrodynamics on Parallel Architectures. The parallel sign is in parallel. It incorporates all of the state-of-the-art hydro methodology that everyone else uses. It just does it much, much faster than other codes do. And I'm not aware of a code in astrophysics that is faster than CHOIA. It shows excellent weak scaling, and that means we can run on the entire Titan supercomputer. So here I'm showing the weak scaling test where you just put the same amount of work on each GPU and you just throw GPUs at it. How fast can you go? So here we're going up to 16,384 GPUs. I mean, you can see it's pretty flat. And that, anyone want to guess how big of a simulation this is? It's a 547 billion cell simulation. And it runs as fast as running a 322 cube simulation, roughly, on a single GPU. Okay, you just have to use a really expensive supercomputer to do it. All right. So, when we initially showed these results, we said, well, look, this is a very restricted calculation. What happens when you include radiative cooling? You'll never get it to scale as well. Well, it turns out that you can use the tricks of the GPU, the hardware of the GPU, to maintain that excellent scaling even by including new physics. Okay, so this is really a key point. So what Evan and I did, initially we implemented radiative cooling on the CPU, and we just used the standard methodology of using a lookup table to do some interpolation to calculate what the heating and cooling rates are as a function of the properties of the gas. That was taking forever. It was taking longer, significantly longer than the hydro was taking in the code, because we were doing the hydro in the GPU, we're doing interpolation on the CPU. Well, it turns out that every time you change a window size in your screen, if you have a smart computer or smart software, what happens is it takes the image of what's in your window and it puts it into a special part of your memory on your GPU called texture memory. Okay, and so as you rescale the size of the window or the image that you're looking at, it does hardware interpolation instantly. So when you read things out of memory, it's automatically doing the interpolation for you. So all we had to do was put our cooling tables into texture memory, and then it was basically for free. So we went from radiative cooling dominating our calculations to being, essentially a free calculation. And so we can scale the same way that we did before. So all of these calculations are as expensive with radiative cooling as they are with adiabatic cooling. So here's the simulation that we're going to be doing. These are, the same kind of simulation I was talking about before. We're doing fixed grid resolution everywhere. So we reach the same resolutions other people are doing with AMR, but we get that resolution everywhere in the volume. We don't need any kind of refinement criteria. We resolve the low density stuff the same as the high density stuff. We use very long boxes so we can watch the stuff as it's stripped out, and we're including radiative cooling with photoionizing background. Okay. So what do we do for the wind? So we're interested in what happens when you have a galactic scale outflow hit some cold material. What happens to that cold material? So what we're doing for the wind is we're pretending that it's a spherically symmetrical hot wind, something like the Chevalier-Clegg model, where there's a certain amount of energy and mass input into a gain region. There's a sonic point in that gain region beyond which the outflow becomes supersonic. The outflow reduces its density in an adiabatic way, so you can see the wind velocity flattens out, whereas the density and the wind temperature go down, and we're just going to pretend we're a kiloparsec away from M82. That's what we're pretending. So we're putting some cold material a kiloparsec away from M82. What's going to happen to it? So here's one simulation. I'm going to show you several of these. So this is the whole box. It's a three-dimensional calculation. You can see the axis ratio of the box quite long. And because you won't be able to see all of the details, I've blown it up here. So let me just run it so I can begin to describe what happens. So initially, the cloud is crushed, and then it becomes shredded through shearing instabilities, and then it's pulled apart. You can see the interior part, the dense regions of the gas can radiatively cool and form these long streamers. But then there's a variety of material, and it's very difficult to see. Out here, these kind of droplets start forming. And there's a lot of rich structure out here in the debris, the detritus of this poor cloud that has been destroyed by the wind. So, there have been a lot of calculations of this. In the past, people have primarily concentrated on what happens to the cloud. What do you destroy it? Does it get stripped? What time scale does it get stripped on? But one thing people haven't really concentrated on is the phase structure of the resulting material. Does it look like the phase structure of actual multi-phase outflows? And so, here are the initial conditions. We have some hot wind. Okay, it's at a few million Kelvin, and it's moving out at 1,000 or 1,200 kilometers a second. And then we have some dense sphere here that where dense is 1 per cc at about 10 to the 4 Kelvin. You can see we put them on an isobar to start, and there's a bit of tapering around the sphere, so it's not quite constant density, and that's why it spreads out along this isobar. It's initially in thermal pressure equilibrium. Okay, so this is an isobar. This is the locus of where heating balances cooling. Okay, so if you're lying along this line, the radiative cooling and the photo UV background are in balance with one another. Okay, and so what happens to the material? You can see that it spreads out along here, and then when it gets dense enough to reach this locus, it spreads out along that locus. Okay, so that makes sense. Okay, so the cold dense material follows the net cooling locus. The rest of the material is in rough thermal pressure equilibrium. Of course, it's not completely in thermal pressure equilibrium because there's this ram pressure from the hot wind that's hitting some of that material. So what happens to the material in terms of the velocity? How fast is the stuff shredded apart? Well, you saw that you get these very dense, thin streamers that form, and that thin streamer lasted a long time. You could tell that the wind was moving past it at quite a large rate. So you could tell already, just from what I showed you before, that the cold dense material doesn't make it up to the hot wind velocity. Okay, 3 minutes? You're kidding me. Okay, go easy on me. Okay, so all of the cold dense material that you saw in these outflows are moving at much less than, oh wow. No, that's 15 minutes. I got 23 minutes. Or 25 minutes. I'm doing just fine. Okay, so all of that cold dense material is moving at only, 150 or so kilometers a second. So it's really moving out at a rate that's much less than the wind velocity. So it's not entrained to the velocity of the wind. Okay, so what happens as a function of density? Okay, and here I'm going to show you 3 simulations of different densities. You can see when you're at low density, so the cooling rate is not very efficient, the cloud is destroyed in a way that's almost adiabatic. But as you increase the density of the material, the cloud material, you can see that more and more of the material can cool out. That makes sense. But also because more and more of the material is at a higher column density, it's harder and harder to push that stuff to accelerate it to the velocity of the wind. So more of the stuff is moving at lower and lower velocities. Okay. And so what happens over time? Well, you actually kind of trade out some of the momentum in these different phases against one another. So what you can do is you can just make a distribution of the mass and the distribution of the momentum. I'm showing the mass here. It says momentum, but I'm showing the mass. Basically what happens is the cloud is initially compressed. You get a high density part of the cloud, and then you kind of eat away that high density part of the cloud. And more of the momentum and mass start transferring to the lower density phases. There's this net momentum transfer from the dense phase to the hot phase. That dense phase is initially crushed by the hot wind that interacts with the cloud, but then as you strip away the cold material, it just goes into the lower density material. Now, one thing to mention, and what you'll realize from the previous plots, is that if you have a multi-phase interstellar medium structure, so the cold cloud that gets hit, if it's not at one density, then the various densities within the cloud will be affected differently by this hot wind that it interacts with. And so one thing that Evan showed in her paper, the code paper for Choya, is that this cloud crushing process that I described earlier doesn't hold up in the detailed way that Klein et al. Suggested does without accounting for the fact that it's the volume filling density that matters for cloud crushing, not the mean density of the cloud. So if you have a turbulent cloud where the mean and the median density are not the same, it's the median volume filling density that matters for the cloud crushing problem. She was the first person to express that. So now what we've done is we've changed from just doing a sphere to a cloud. This is a turbulent cloud. And you can see, and I'll just run this for a little bit and then I'll show you a higher resolution version, that the destruction of the cloud is much different. And the reason is that there's a larger volume of the cloud at lower densities. And that stuff's a lot easier to strip out of the cloud with the hot wind. So let me show you a high resolution version of this. This is a 1.2 billion cell calculation, just zooming in on the one cloud, just to give you an idea of the structure that develops as you hit this turbulent cloud with this hot wind. Okay, this really is the multi-phase structure of these galactic outflows if you could resolve that structure. Okay, so when you see your simulations and you're pushing out these, thick streams of material from your galaxies, realize, it's not really going to be like that in detail. It's going to look a lot like this. And so when you're talking about things like the equivalent widths of absorption lines or the detailed ionization properties of different ions that you might see, realize that really there's going to be a variety of densities and velocities and metallicities, and the mixing of this gas is all going to affect those results. So please, try to hone in on that. I just wanted to say, let me just skip because I really am now running out of time. You can see I've got a lot of things, but I'll finish up here. So, what you can conclude from the simulations that I showed you previously is that all of the cold material that's moving at large velocities in observations likely didn't originate near the galaxy. It's very difficult to take a cloud, shred it, but keep the cold phase moving at a very high velocity by pushing on it through a hot flow. And I think most people agree on that statement. Maybe some people don't, but I think most people do agree on that. But one thing you can do is you can take that cloud, you can shred it, and as you shred it, you mass load the hot phase of the wind. So you take dense material and you put it into the hot phase. That's what happens in our simulations. Okay. Then what happens to the hot phase? Well, the hot phase is then mass loaded. That means its density is higher, and the radiative cooling timescale of that gas will become shorter. And so what Todd Thompson did is he did some analytical calculations of a Chevalier-Clegg-like model where he accounted for the fact that as you take a hot wind and you make it denser, eventually some of the material can radiatively cool out of the hot wind. And that material will be moving at relatively high velocities. That's what he's showing. This is mass loading in this direction, mass loading in this direction. It can cool out, and it's moving at relatively large velocity. Okay, so that might be able to explain what you actually see in observations rather than trying to shred clouds near the disk and push the cold material out into the halo. And so he presented this kind of picture where there's some hot, fast wind that eventually cools out at, say, 10 kiloparsecs, beyond which there's some decelerated cold wind. I wouldn't pay too much attention to all this. I would rather look at Drummond's talk. He was actually simulating the processes out here. I think what we really need to do, and I know he's working on this and Evan's working on it too, is to really simulate what happens within this cooling radius. If we take a disk galaxy and we simulate the disk galaxy, we allow for an outflow with enough resolution so that we can capture the formation of cold, cooling instabilities in the outflow. What does that look like, and can we compare it with observations? That's a really tough problem to do. So let me just summarize, and thank you for letting me run over 2 minutes. Star-forming galaxies, as you all know, are very, very complicated objects, and their outflows are very complicated. So we'd like to understand these, and I think people are doing amazing work, but I think we need to attack the problem on different scales. Much like we're attacking subgrid physics and star formation on small scales, we need to be doing the same kinds of collaborations with the CGM and outflows. To tackle this problem, and many other problems, Evan Schneider, my student at U of A, wrote Choya, which is an amazing code. Can run a trillion cell calculation. Okay, so there's really a lot of power in this code that we can apply to interesting problems going forward. And we've looked at this multi-phase outflow problem. We're in rough agreement with most others who have looked at the same problem, but we went a little bit further, I think, and we looked at the multi-phase structure of that material as it outflows, and we really looked at how mass and momentum are exchanged between these different phases. and tried to get a feel for what might be going on physically in the multiphase outflows around galaxies. Thanks a lot. Thank you. So people have written AMR codes on GPUs. The challenge is to keep it in an efficient calculation. So the way a GPU works is it has 3,000 small cores. And so you want to keep all those cores busy. So you can imagine that if you did AMR and you had some region that you'd refine that's relatively small volume and a small fraction of the total number of cells, with short time steps, keeping the GPU busy and all of the GPUs busy by subcycle, it's a difficult problem to solve. So a patch-based AMR where you just resolved a huge block and fed that to additional GPUs, that might work. But if you just do 2x2x2 kind of AMR schemes, that's going to be a bigger challenge to take care of. Now, static mesh refinement is easier to swallow, and so I think we've thought some about how to do that. But we haven't fully exploited the fact that we can do these very large fixed grid calculations yet. So until we get to the point where we run out of things to do or really can't answer the problem, we're going to stick in that regime for the time being.
Let's go here and then to Joel. Can you wait for the mic?
So I didn't hear you talk too much about the nature of your win, but is it possible to do, how hard would it be to extend to charged particles and relativistic particles and that would kind of at least seem to simulate the kinds of things that go on in supernovas and AGN?
Yeah, so it would require some kind of particle scheme. So you could change this code into a pict-base code or some kind of hybrid pict scheme, particle and cell scheme. The same kind of numerical operations are there, and so it's possible to do. It's something I've thought about doing, but I don't have, if you're interested, we can definitely talk. But anything where you have a fixed volumetric grid and you're not having to change the properties of the cells, then you can probably get away with using a GPU with some good increase in efficiency. But there are lots of issues to worry about that I can give a whole talk on that. So, yeah.
Ever since the old MacLowe et al. Paper, people have wondered to what extent metallicity follows the general outflow. Mm-hmm. And especially the strong, robust data on the mass metallicity relation for dwarf galaxies is an important test for theory. So any wisdom and any possibility of including in your scheme fractional metallicity outflows?
Yeah, so I think there definitely is. So, it's just another field we'd have to follow. We'd have to change the cooling scheme. And so there are some issues there, but nothing that isn't insurmountable. I think it's definitely important, when people talk about chemical enrichment of dwarfs and they're looking at recycling and other processes, how do you know that when you send the metals out in whatever phase structure you send them out in, that A, they maintain that phase structure, and B, when they come back in, are they going to maintain the phase structure they had when they went out? And I think those are all open questions. Even though we get, the right basic answer, some people seem to get the right basic answer, I'm not convinced that, there isn't some kind of mixing problem, the overall metallicity, if it mixes with low, metallicity, cosmological infall efficiently, is that going to change the story? So I think it's something to look at in a lot of detail. So,
do you want to do one more quick one? We've got some time.
Camille? Yeah.
That question, what is the time scale on which you see those hot metallitic phase pools?
Can you just repeat the question?
Oh, she's interested in knowing how long it takes the hot outflow to cool. I would look in Todd's paper. I forget what it is, but if you're moving at 1,000 kilometers a second, it's the time scale it takes to go to 10 kiloparsecs. That's about the cooling time scale of the wind. Okay. All right. Thanks again. Thanks a lot. Oh.